Hi guys, we're going to continue with the problem that we started earlier this week, and we're going to do a couple of things. We're going to confirm the answers that you should have got by looking for the displacements of the two nodes, and then I'm going to go through and show how we would use the force method in conjunction with the virtual work method in order to solve for those two displacements if this structure becomes statically determinate. That is, if we add the support on the right such that the support on the right would become a built-in support. So let me just bring up the notes. So this is where we left off last week. This number here, let me use the right thing. So this number here, I got off by a factor of 10. Okay, this should be 34.9 millimeters. So this was the force in BY, and I had challenged you guys to find out the forces in the other two directions. So let me just bring my code up. That's probably the easiest way to show this. So I'm going to move this up. Here we go. So this is the code. We've got the way that I've done this is I've done this sequentially, and I'm going to go through methodology of how we do this. So here we go. I've got so this is the virtual forces when loading at BX. So you've got all of these forces here, and then I've got the force under real loading. Okay, same down here. I've got the one for BY is here, and then the DX and DY here. So the displacements that we've got are 6.94 millimeters when in BX, minus 34.93. That's the one that I got wrong for BY. 58.705 millimeters in DX, and minus 16.412 millimeters for DY. And up here you can see all of the intermediate forces. We've got those reactions, and we've got the internal virtual forces in each of those members. So I'll check if there's a mistake or not in there later. I don't think there is, because I've already gone through this problem. But I want you to go through here, compare to the answers that you guys have got, and then we're going to continue now. And you'll see that I've given you guys a starting point for this notebook, and I've given you the starting point that includes where to put your free body diagrams and where to put your method of joints. So this is presupposing that you've already done these sets of calculations. These are my calculations for the free body diagram and method of joints that I did last week. Now, let's just have a look at the free body diagram for a second. I had a student in office hours questioning or getting confused by the way that I do my functions, or just getting confused by functions in general, I guess. So let's bring up a function. Okay, so we can skip through this bit. If you're golden with functions in Python, then we don't need to go through this. So let's say let's just do a simple function that's going to add the two numbers given to it together and multiply by 2. So say I've got, let's call it def, my function, a and b, and we put 2 letters into it. The output is just simply going to be, well, I'll say in the middle, we'll say c is equal to a plus b multiplied by 2, return c. Okay, and if I now have the function, this just means that I can always do those operations. I can say print my function 2 and 3. Okay, so 2 and 3 added together gives 5, multiplied by 2 should be 10, and it gives me 10. Okay, this is why we use functions, because then I can repeatedly do those operations, and when I've got the free body diagram here, I want to repeatedly do these steps, these 3 calculations. I've got FAX is equal to these here, that's the reaction at AX is equal to these external forces, the reaction at CY is equal to these external forces, and the reaction at FAX is equal to, FAY is equal to these external forces. So this is confusing if you don't understand what dictionaries are in Python. Dictionaries are a way that we can store data in Python. There's lots of different ways you can store them in lists, which is similar to arrays in MATLAB sort of. We can store them in sets, or we can store them in dictionaries, and dictionaries are really useful for this purpose. So with the way that I've chosen to describe my free body diagram, I've said my So it's a def my FBD, for example, is a function of something called reactions, which we put in. I just called this f here. And then I'm going to do my three equations. So I put equation 1, equation 2, equation 3, and then I'm going to return my reaction. Sorry, this should be an f up here. So let's say that the input to this function is going to be the external forces, and it's going to return the reaction, which I'm going to call r. So I could choose to put both f and r, have them as lists, and I could then say, okay, this assumes f and r are lists, and that means that I have to be careful about the order in which things are stored in there. So let's say I want to put these three equations in there. Well, I've got 1, 2, 3, 4, 5 external forces. So I would have to say F is equal to, and this is just a comment. Let's say I've got F by, F bx, F dy, F dx, F cx, for example. And then that means that I've got to put F in there with those 5 numerical values in that order into my F matrix and then onto my F object. When I then want to go for equation 1, I can see equation 1 says the reaction AX is equal to minus FCX plus FDX plus FBX. Now, if I want to use this, I have to say, okay, I'm going to make reactions is going to be a list. And I then have to decide the order that these reactions are going to be in. It makes sense to say AX, AY, and CX. So I'll say the first element, which is FAX, is equal to minus, so FCX, well, FCX was up here, so that's actually F0, 1, 2, 3, 4. So I'd have to say, let's close it, let's put an open bracket here. I'd say equal to F4 plus FDX, which is, okay, which is this one here. So that's the 0, 1, 2, third elements. And then I'd have to put the last one in, which is FBX, which is actually the second element, which is the index 1 in this. So I'd have to go through. Now, this means I always have to put those items in the same order and remember what they mean. And it's not very intuitive when you're reading the code to think, okay, F4, I had to go up here and see what order they were in. So that's why I choose to put these in as dictionaries instead. So dictionaries are a way to store data where we store data with a key and a value. Now, you guys should be happy with this because it's covered in the Python intros, and this is just the basics of how we do programming. But dictionaries, so these are defined in Python by starting out with curly brackets, and we say a key, colon, value. That's one way to start a dictionary, or we could have a say equals key 1, value 1, and then we put a comma, key 2, value 2. Now, we don't need to remember the order because the key could be a number, the key can be a string, the key could be another object, but we're going to say, okay, I'm going to call these by the things that they sound like. So let's go down to this next cell down here, and I'm going to say this is storing R as a dictionary. So let's just put some values into here. We'll say R is an empty dictionary. I can do that, and then I could populate values in there. Or I could say R is equal to, let's say I have the values. Let's say I happen to know RAX is equal to 100, RAY is equal to 200, and RCX is equal to minus 50, for example. Okay, these numbers are meaningless, but I say I want to put them in there. I'll say that AX is equal to 100, AY is equal to 200, and Cx is equal to minus 50. So I've now got a dictionary called R, and if I want to get, say, the AY term out of it, I don't need to remember where it's stored. It doesn't matter what order these are in here. I can just say print R, and then I use the square brackets to tell me which part to take, and I say, okay, I want to know what AY is. Gives me 200. If I want to know what CX is, gives me minus 50. Okay, that's why I think a dictionary is a better way of storing things like R and things like F, because it means that you can put human interpretable labels to the way we store things. Those are the keys to the dictionary. Okay, it's just a better way of storing data. I don't know if MATLAB has anything similar to that. Once you move away from MATLAB and you realize what a real programming language is, you'll realize how good it is to store things like this. Okay, so that's why I store things in dictionaries, including my free body diagram and my method of joints. Okay, so if you haven't bothered to write your own, you can just screenshot here and put them in, but please don't do that. Please just try and understand your code. Please try and make sure you've written your own. Okay, so these are what you guys should have already got, and we're going to now go through and try and solve the rest of the problem. Okay, so we've solved for the internal forces of the structure if we've got the statically determinate case. Well, in fact, let's go through this. Let's go through the forces in the statically determinate case. This is my real loading. I've got P1, P2, and then my force, my external forces, again, is a dictionary. So it's dy. Well, I've got those 5 forces. So my real loading is dy is 0, dx is P1, bx is 0, by is minus P2, and cx is 0. This enables me to get the reactions and the internal forces in the real structure. So I can say get reactions, R is equal to FBD of F, and I'll do print reactions R. I, for some reason, deleted the D there. There we go. So that's, here we go. And again, the reason dictionaries are handy means I can define a function like print reactions. And what this says is go through my dictionary, work out what the key and the value are, and then just print out the reaction at this key is equal to this value. That's why it's a useful way to store these. So I've got my reactions now down here. I can then get my internal forces. So that MOG needs R and F. Doesn't like that. Tuple has no. It's because I've just copied and pasted some code and everything. Oh, there we go. That's why. It's because actually my method of joints gives me 2 things out. Method of joints gives me the forces, and it gives me, so we're up here. Method of joints gives me the forces, and then it gives me the extension. So I've got F, DL. So I need to say forces and extensions. There we go. Okay, so we've got this, and I've got the internal forces of the structure where we've only got the roller support. Okay, so let's do the force method. Let's work out what the redundant support is on this structure if we then take the node on the right and replace it with a built-in. Okay, so we've got our structure now. We've still got the real loading, P1 and P2. Is that the right way around? That might be, that's the wrong way around, isn't it? That's P2, that's P1. I've got my reactions here, and I've got this redundant reaction that we're trying to determine. So I want to determine this. So we now need to work out how much the structure moves to the right under the real loading. And it's useful, and so what we've already got, we've got these 5 placeholder forces. So the way that we're going to do that is we've going to use the virtual work method. So we're going to determine this displacement, delta here, by applying a virtual force of 1 Newton here. We'll say okay, then whatever that 1 Newton force gives in terms of internal virtual forces, when multiplied by the real extensions, which we've just got here, has to be equal to 1 Newton multiplied by this number. And then that gives us delta. So let's go through and do that. So we're going to say this is determine the redundant reaction. Remember, delta is the displacement of the structure if this reaction was equal to 0. Okay, so the way that we do that is we apply a virtual force here. So I'm going to apply an internal force. So the way I'm going to do that is I'm going to copy this line up here, which is define my loading. And I'm going to call this F star, which is my virtual vector. I'm going to make everything 0, except for CX. And again, this is why I have it as a dictionary, because I don't want to have to look around the code and remember, CX, is that the 5th or the 4th element? I know where CX is. It's the one that's called CX. Okay, so this is now no longer the real loading. This is the virtual loading at CX. And what I can then do is do the free body diagram to work out the virtual reactions, and then I can work out the virtual internal forces. So I'm just going to copy these lines. I'm going to call this R star, and I'm going to call this F star, and I don't care about what the actual deformations are. So let's change these to R star. So the way that I've defined print forces is going to tell me what those deformations are anyway, but we don't care about them. So I'm going to just put a line here to just change my output. I'll say with a virtual force of 1 Newton at CX. Okay. Oh, it's because what I've done here, I can see it. These numbers are the exact same reactions as up here, and that's because I didn't put the actual virtual force into my free body diagram. So let's change this to F star. There we go. Okay, gives me my reactions now. So the load is reacted at AX, and then and then I've got -0 and 0. That's just a numerical issue there. That's fine. It's not even a numerical issue. It's just the fact that I know that in the free body diagram, one of them is -0 plus 0 plus 0, which gets interpreted as -0. Doesn't really matter. What we've also got is all of the internal virtual forces, which are these values here, and those are given by F star. So we can then determine the internal virtual work. So what I'm going to do is I'm just going to comment these lines out because I'm printing out too much stuff. Let's comment these out. Remember, the internal virtual work is equal to these virtual forces multiplied by the actual extensions that we have. Okay, so let's multiply these together. We can multiply these together using a sort of a nifty dictionary equivalent of a list comprehension. Let me just move something out of the way. I've got to remember the syntax of this because I sometimes lose this. Here we go. So I could write this out as, I could write down every line. I could say I've only got 5 members, I could go through them, but actually I know that for more complex problems I'm going to have more of these members together. So what I want to do, I want to say for every internal force that I've got, find the associated extension, multiply it by it, and put this in something new called UI star, or internal internal virtual work. So we're going to do this way. I'm going to say UI star, and it's going to be a dictionary because that's the way we store things. So it's going to be dictionary. I tell you, I'm going to show you a little thing first. Okay, so let's say for key value in F star. So there's I could just loop through. Apparently, I can't do that. Can't unpack. Oh. There we go. Okay. So if I want to loop over all of the things in F star, which is a dictionary, I can say for all of those things, okay, for every key and every value in F star, I'm then going to print out, and I'm going to say my key is 1, value is, yeah, that's okay. Yeah, it is right. It's fine. That's fine because I've called these members 1 through in my method of joints. I've called them 1, 2, 3, 4, and 5 because I just numbered those. I numbered them in that order. Okay. I don't need to care about what they correspond to because I've also called the DLs and I've numbered them according to the same scheme. So what I'm going to want to do is I'm going to say, let's say UI star is equal to an empty dictionary. That's my internal virtual work. I'll say UI star. The value at, let's say the value at the key is going to be equal to F star. Nope. I could say F star key, but this will still work. Multiply by DL key. If I do this, it's going to then give me a new array called UI star. There we go. This is now just all of my internal virtual work. This is one way of doing this. There's about 1,000 ways you can take an array and multiply each different element. I could also do this with a single, effectively a list comprehension. I could say UI star is equal to a dictionary. I've got to remember how I wrote this. It's been a while since I've written one of these. Let's have a look. There we go. In fact, and what you might notice is in this comprehension here, I say get the value out, but actually I never use it. So I could say here, I'm going to make a dictionary, and which has a key, and the value is going to be F star key multiplied by DL key for key in F star keys. Okay, and just check these numbers shouldn't change. Let me just copy that line here. There we go. It doesn't matter how I do this calculation, I end up with the same answer. Okay, that's fine. So this line, this maybe shows what's going on a little bit easier, but this is a single line, so I like this method. Okay, so, but what I've done there is that's worked out the internal virtual work within every member of the structure. What I really want is the sum of all of those things. So I want to add them all up together. I could have done that in my loop. I could have gone through and added through each of those in a loop, or I can just say the total UI star. Let's say total UI star is equal to the sum of all of the values in UI star. Okay, and you've got to tell it to sum the values. So let's say print. Oh, it's because I put this with an underscore here. So down here it says name error, UI star is not defined, and that's right, it's because I've called it UI star here. So it says the error is in line 97. UI star, I haven't called it that, I've called it UI star without an underscore. In fact, I should probably, no, let's just leave that. Okay, so that's my total internal virtual energy, that's got units of joules. Because I supplied a virtual force of 1, that's also then the amount the structure is going to move to the right. So that's actually just equal to my delta. So I'll say delta Cx is equal to total UI star. Okay, so that's the amount the structure moves to the right if that support were not present. If that support were not there, we've got that first delta. Now what we can do is work out how much the structure would move back if we had a unit force of 1 here, okay? Now, because what we want to determine now, so what we just determined here, that big delta Cx, we used a virtual force of 1 here, because we wanted to determine how much this point moves to the right because of P2 and P1. Okay, so that was a virtual force. What we're about to do now is work out how much the structure would move back if we have a force of 1 here. Okay, that's not a virtual force because we don't care about P1 and P2 now. We want to know how much the structure will move if I push it with 1 Newton. So it's going to be a unit force. So we can still calculate things using the same way, but we've got to be careful that we're not, when we're trying to determine the total internal energy, we've got to work out what the extensions are due to that 1 Newton, not due to P1 and P2. So let's make a F unit. So let's call this with a unit force of minus 1 Newton at Cx. Okay, so we've now got that unit. I can just do the same thing here. I'm going to call this F unit. And I'm going to copy the reactions down here, get F star. I'm going to copy all of these lines. Let's just copy them down. I'm going to change this to be our unit, which is the internal reactions. If we have a unit force of 1 here, change all of these stars for units. Now what I also want to know, okay, whereas I didn't need to know that before, I want to know what my actual deflections are. If I push here with 1 Newton, where we push here with 1 Newton, I want to know my actual deflection. So I'd previously said don't have these answers. I now want to know. Okay, so I want to have DL unit coming out. Okay, so everything else is the same. Let's check we've got everything down here. Now determine the internal energy due to 1 Newton. Okay, so we have down here, I'm going to call this UI unit. Same here, I'm going to say this is equal to F unit multiplied by DL, and I actually need to multiply by the unit force because we're going to remember that actually now we're looking at a slightly different definition. We're looking at the real internal energy that would be stored if I pushed back here with a 1 Newton force. And I've also got to remember to multiply this by 0.5 or a half. Okay, and let's just consistently, let's change this to unit here. And I'm going to change all of these. I've just, again, I've not put an underscore in one and I should have done another. Okay, so there we go. We've got a small number here. Okay, small amount of internal energy stored here. Now, what we're going to do is we're going to say, okay, I actually need to remember the definition of internal and external energy. We had a half within each of these because that was the definition of real internal energy, and that then therefore has to be equal to the amount that's moved in this direction, which is going to be my lowercase delta multiplied by my F unit force multiplied by a half in this case. Okay, so we've got to put that half there. They both cancel out. So it's not an enormous problem if we don't put that there at the end of the day, but we've got to remember to do it either in both cases or not in both cases. Okay, and my actual unit force was -1. So I'm going to call this lowercase delta Cx is equal to total UI star divided by -1 multiplied by a half. I'm just going to get rid of this line that was just demonstrating what we had there. Let's just see what the sizes of these two are. Okay, so I'm printing out what the movement is without the reaction, and then I'm going to print out down here the lowercase delta. Now we should expect this second one to be much smaller. There we go. Okay. Those numbers don't make sense to me. Let me just check because I'm expecting the second one to be quite a lot smaller. So let me just have a look and there we go. It's because this number down here, I haven't changed this to a unit. Okay, this is my internal virtual energy. I need to change this to my internal unit energy. So that's the real energy there. If I run this now, here we go. So it says that without the support, the structure is going to move to the right 13.9 millimeters. With just a single Newton reaction, it moves to the left by 37 nanometers. Okay. The actual reaction is just the ratio of those two together. So our F Cx is equal to delta Cx divided by delta Cx. Okay, so this has told me that for the real loading on this structure, that's my redundant reaction. Okay, that's how much my reaction FCX is equal to. So that took me from here down to here just to determine that redundant reaction. So what I'm going to do is I'm going to tidy this up a little bit and I'm going to put this into a function because we're going to need to do this operation a few times. So let's say def get redundant due to some applied loading. And that means that everything down here I have to indent. Okay, and I'm actually going to comment out all of these lines because I don't like it when functions say things. I don't like it when functions print out stuff to screen. Let me unplug my iPad for a second and charge my pencil up. So I'm going to comment out all of these lines. So that my function that I've defined doesn't actually say anything. Okay, when I run this, it defines the function, doesn't actually do anything with it. So I'm going to take this up here, which is defining my loading, and I'm going to go down to a new cell down here. Okay, so that's my real loading, and I'm going to say let's determine the redundant reaction. What did I call it? I called it get redundant reaction F. It says get redundant reaction isn't defined, and that's because I can't spell properly, so let's put a D in there. There we go. So this is running, it's not throwing an error, and the cell has completed by this number in here. Okay, so I know this is run. Let's just check that I've got the same value out. Print FCX, and I'm expecting this to be minus 375. Doesn't like this. Doesn't like it because I didn't define my function properly. That was stupid. So this function up here, I told it to calculate FCX. I need to tell this function to actually return this. So I need to say return FCX. So this function, what I just called here, it would have done all those calculations and then ignored the answer. Now if I've got this up here, let's rerun that. Here we go. And I get the correct value out at the end here. Now, when we solve part 2 of this problem, we're going to need to do this a few times over. So let's do the next step. Now we've got this redundant reaction. Let's work out the internal forces in this structure. So what I want to do is I'm going to take let's update the applied forces. I'm going to have previously where I had FCX was equal to 0, I changed this to FCX. And then what I'm now going to do is I'm going to get the reactions, get the real reactions. Now this is if we've replaced the support on the right with a built-in. We know what the redundant reaction is because we just got it here. Get the real reaction, which is and then once we get that R, we can get the internal forces. Oh, it's just called print forces, that's why. Oh, it's because I called that uppercase F. That should have been a lowercase f, I think. No, I know why. I've made the same mistake that I made earlier. What it's saying here is tuple object has no attribute keys. Okay, tuple is just something that's stored between curly brackets. Now, if you've got a function that's supposed to spit out two things and you tell it only to take one, it'll only take one. This function spits out two things, f and dl. Doesn't like that. Why doesn't like that? Okay, I can see what's going on in print forces. Oh, okay, that's stupid. What I've done here is print forces is something that I defined to print out the internal forces. Defined it earlier. Okay, I've called my internal forces lowercase f. My uppercase F is my applied loading. What it's trying to do now is trying to use this print internal forces to print them out, and as part of that function, which you guys can go back and look at, it prints out it also works out the extension of each of them so it can print them out. And so as part of that, it needs to look up the length, which is defined up at the top here. And it doesn't have, and those again I've defined in a dictionary. I've defined these as size 1, 2, 3, 4, and 5. So what it's trying to do is trying to look up one of the keys from F, which the first one it's got is dy, and it's trying to find the length for that. And it says, okay, there ain't no, it says key error dy, there ain't no dy in L. Okay, so all I need to do is say, okay, I got my internal forces out and I called them lowercase f. I now need to print out lowercase f here. Okay, so yeah, they look good to me. Okay, we've got some numerical stuff going on here, which is interesting. What it's telling me is that we've got effectively members 2 and 5 are effectively zero force members, because it's telling me that I've got piconewtons in those, which is I should have put a tolerance in this to print these out. But we've got the real forces in here. A good way of checking whether we've done this properly, and this is why it's useful to maybe do this as coding so we can check things out. P2 is the vertical force, P1 is the horizontal. If I change P1 to nothing, I should get symmetric forces here when I run it, and when I do I not? Yes, I do. I get symmetric forces. Okay, so member 1, yeah, I'm going to leave you guys to figure out which members. I think, did I say that last time? Did I go through which member was which? Yeah, I did. I called them member 1, 2, 3, 4, 5, and that was in the table I gave earlier. Okay, so I'm actually going to leave this here now. We're going to spend another short lecture going through how we do the next part, which is determining the displacement of nodes B and D subject to this real loading. Okay, so what we've done here, this is the internal forces and all of the real extensions in each of these members due to the real loading. As long as I change this back to the real load, I'll run this. Okay, I've got all of the real forces and all of the internal extensions. Remember that what I want to do to determine the displacement of nodes B and D is work out the internal virtual forces caused by an external virtual force of 1 Newton at B and D, and then multiply those virtual forces by these numbers here, add them up together, that's my displacement in the direction of that virtual force. Here's where we have the issue. When I apply those virtual forces, I need to determine the redundant reaction according to that virtual force. Because what I remember when we went up here, when we used even just in the force method, when we worked out the load to the right, we had to work out the reactions. Okay, so the first step of the force method is work out what the loading is, work out what the reactions are, work out what the internal forces are. So when I apply a virtual force of 1 Newton to my structure that has 4 reactions, I'm going to need to work out the redundant virtual reaction. And it's almost like I thought about this and thought, I've done this once, so why don't I take all of those lines of code and put it into a function? Because I'm going to have to do it 4 further times. Okay, so I'm going to leave this here. I'd like to see if people can get to this point. If anyone can go do the next step, that would be superb. Okay, I'm going to leave this here. I will record the next lectures, but I probably won't release until next week. I might not get to doing the internal redundant members. I might just leave this and do a couple more examples just to let everybody catch up. I hope everybody's having a wonderful week, and I hope you all have a wonderful weekend, and I will probably release 2 more lectures next week, and that's this module over. Okay, take care guys, enjoy the virtual work method, and I'll see you all soon. Take care.